LED counter using the Tang Nano 9K. So first we create a new project and you can name it counter. Here we will be using this device for our LED counter. So we go on to create our new file. We will make this a Verilog file and we will name it counter first. Okay. Where we will include our input clock and our output being the I/O voltage. Continuing from here, we will label our count value as a parameter which will then be equal to 13.5 million more or less, which is the amount that will be equal to 0.5 seconds for the counter. Then we will make two more elements that are called count value register, counter if loop, which we will begin to write right now. So now we start by creating the pause edge, which will be designated by the clock once again. And we begin writing our if loop. If count value is equal to the count value. So if count value reg is equal to the count value that we wrote above, which is the time needed for 0.5 seconds, then once again begin. We designate our pause edge as the clock and then we begin. Here the if loop states that if the count value reg is less than or equal to the count value, then we will begin to add a bit to count value reg if the statement is true. This statement will then add to the count value reg value. And then our count value flag will not change and instead will be given the designation as 0 or in this case a no flip flag. To write our other statement, which is if the above statement is not true, in this case if the count value reg exceeds our designated count value, then the statement will instead change our count value back, or our count value reg back to its initial state, and then change our flag to 1 bit or to initiate the flip flag. write the IO flip, which will cause each LED to either turn on or turn off. Now we will designate another variable called IO voltage reg or reg, which will be equal to 1BO, which is our initial state. And then once again, we will write a simple if statement. Here we designate our pause edge as the clock. If now here, if our count value flag is equal to 1 bit, as we have designated it, then our IO voltage reg will then change its state or change its designation as is written here. And if that is not the case, then IO voltage will have no change, and it will just be designated back to its original self or reference to its original self. And this is the basic code that we will be using for our counter. This extra line will just be to make sure that there is no confusion with our IO voltage. And then we end module. Uh, of the LED counter. Here we designate our counter value as 13.5 million, which is approximately what we would need for 0.5 seconds. Then we write our count value reg and our count value flag. Our count value reg then has a 23-bit size or 24-bit size. Then we start with our if loops. Here we designate our pause edge as the clock, no neg edge is present. And in our if loop, if our count value reg is less than or equal to our count value, if this statement is true, then we will add 1 bit to our count value reg, and our flag will also be designated as 0 or no, 0 bit. If this statement is not true, then our else will come in our else. If our count value has arrived to the same value that we designated here, we will return it back to its base state. And then we will also change our flag to show as 1 bit, which will then be used in the second portion of the code. Here, our IO voltage reg will be designated as 0 or no bit, and we will write another simple if loop that will look for the count value flag if it has changed to become 1 bit, and if it has, it will cause IO voltage reg to change or a negation with the bitwise function, which will cause the LED to change its state. And here, if this value has not changed, if this flag is not present, then the IO voltage will just designate back to itself or to the value it is currently. Once again, we write this statement down here just to avoid any confusion in the code. For it to stay in a position that we do not want, it would return to what IO voltage is, and then we end the module, which we will simply name JS6. Now, for JS6, this module will be used to count how many phases or how many LED will shine or how many blinks we will get or receive for the counter. So we designate our different variables as NR. We will have CLK for clock, and we will have Q. Then we will mark NR and the clock as our input values. And our output value will be Q. And this Q will have a size of 4 bytes because that is how many bytes we will need to count up to the value that is, or at least this size can change depending on the value that you want to count to. For us, we will be counting up to 14, and 14 in bits or in binary code has a size of 4 bits. And so that is why we will only be designating these amount of bits to the code. Our simple if loop, so always at, this time we have both a pause edge, which is our clock, and a neg edge, which is NR. Then we begin the if loop. The if loop will state that if NR 0 or is, then NQ will be designated as 0. Else if NQ is then equal to 14, which is the value that we are counting up to, and Q will also be designated to 0. And then finally, if none of these are the case, then NQ will have 1 added to it. And then once again, always at. Here, once again, we make it so that the value reverts to its original state once the cycle is finished, just to avoid any problems or errors in the code. And then we end the module. File, which we will call it test. Now here in test, we will call on the previous 2 modules that we have created. And this will be done by first we create a separate module that we name test as well. And we designate the variables that we have used in the other modules. So we have NR, we have clock, there's Q, and we have our I/O voltage. And then once again, we designate which are input and which are output variables. So input is NR. Clock. And our output, once again, will be a 4-bit size. So here, 3, 0. And this will be the value that is used for both Q and for our I/O voltage. Is U1. This is just how we will call onto the counter module that we have already written. And then we will designate the different variables from within that module to refer to one of the modules or one of the variables that we have designated here. So clock will then refer to CLK that we have written up here. And we will also do this with I/O voltage. And then we will close this bracket as well. And then we will do the same thing. We will call on JS6 as U2. Then once again, we designate the different variables from within JS6 as the variables that we have written here for the test verilog file. So NR will then reference NR. Dot clock will do the same. Or we'll reference I/O voltage, I'm sorry. And then Q will reference Q. And then we end the module. You could have either run synthesis individually or save them and run the synthesis together. Once this is done, we can then open up the floor planner. Yes, we will create. Now for the floor planner, we will go to our I/O constraints. Now for our I/O constraints device, but now I have fixed that. So once again, we save our modules, we run a synthesis. Once we have run our synthesis, then we can open up the floor planner. Here in the floor planner, we can look at our I/O constraints, and here we can give them the different inputs, which will correspond to the inputs that are available on our Tang Nano. So here we look at all our input and our output that are vital to making the entire module work. So here we have these designations that we get from the manual with the Tang Nano, 13, 14, and then NR will be 3. So we save these constraints, then we close. And once we have this, you can finally start with the programmer. Now, let me connect the device. And use the floor planner. We can then go to the programmer. Here you can see it picks up the device. Save, as we will be just using the simple SRAM operation, and then we can just program / configure to the device. And once we have done that, see that the LED works in the manner that I am showing in the video. And that is how we set up our simple LED counter